Hello everybody, this is Shivaji and we are critically evaluating recursive function call versus iterative approach. So far we have learned what tail recursion is, and we have found that tail recursion is just equivalent of writing a loop. No extra overhead or burden is there with the tail recursion. And we have also seen that in case of non-tail recursions, it's better to write loop. If you need to implement a particular logic using a non-tail recursion and you have an equivalent loop to solve the same thing, then it's better to go with the loop, because the non-tail recursion is going to bring in the overhead of stacking activity in the memory. Now we need to understand when exactly we need to go with the recursion instead of iteration. So there are situations when we explicitly need a stack in order to solve a problem. So in such cases, we would require to implement the stack by ourselves, and that will just increase the number of lines of our code in our program. But since we know that there is a stack in the memory that the system creates in order to maintain the recursive call, so we can use that stack instead in order to preserve our values and can do away with the writing of our own explicit stack. So that will just reduce the number of lines of code, and we will be beneficial in such cases by using recursion. Let's have this example. Say we need to write a program in order to print the binary equivalent of a decimal number. The traditional way for doing this is just to divide the decimal number by 2 and collect the remainder and print it in the reverse order. So say we need to find out the binary equivalent of decimal number, say 12. Then we will go on dividing it with 2 and we find that the remainder is 0. We need to store this because this is the least significant value. And then again we will go and divide 6 by 2 and we get 3. So again we are having 0 as remainder, and again we are dividing 3 by 2. So here is 1 and we have 1 as remainder. Again we divide it by 2, we get 0 and 1 as remainder. So now if we print in the reverse order, then we get the binary equivalent of 12 as 1100. This is the binary equivalent of 12. But in order to perform this programmatically, what we need to do, we need to have a stack in order to store the remainders. So we will be using the stack, otherwise it's not possible. As you can see that on each division, after each division, we need to store the remainder and we need to get it in the reverse order. So what we will do, we are getting the 0 here, so we will have a stack and we'll push 0 into the stack. Then we are again having 0 as remainder, we'll push 0 again, and we are having 1 as remainder here, so we will be pushing 1 here, and again we have 1 at the last time, so we'll be pushing 1 again. So now from this stack we will be popping the elements and we will be printing the elements into the console. So stack is very much required to find the equivalent binary number for a decimal. Without this stack we cannot do this. So in order to implement this stack, we need to write code and we need to write the push operation, pop operation, and all the maintenance has to be done for this stack. But if we are going with recursive solution in order to find out the binary equivalent of decimal number, then we can do away of writing this stack explicitly, and we can use the system generated stack for maintenance of recursion, for keeping these values, for keeping our desired values that we need to preserve for our program. Let's see how we can do that. Now before going to that, you need to understand one more thing, that we can find out the binary equivalent of decimal number just because of the fact that it's recursive in nature. If you can see that, say I'm having this 10, I want to find out the binary equivalent of this 10, and binary equivalent of 10 is actually binary equivalent of 5 and then the result of having this 10% 2. Binary equivalent of 5 is 101 and 10% 2 is 0. So you can see that this is the equivalent of 10 in binary. Now how do you find out the binary equivalent of 5? It's again recursive. So binary equivalent of 5 is actually binary equivalent of 5 divided by 2, that is 2, and then we need to just print or have this 5% 2. So binary equivalent of 2 is 10 and this 5% 2 is 1, So binary equivalent of 5 is 101. That's the binary equivalent of 5. Now how would you find the binary equivalent of 2? That's binary equivalent of 1. That's 2 divided by 2. And then 2% 2. So it's recursive. So we can just use the recursive function call in order to find out or print the binary equivalent of a given number. First of all, what we need to do is to check whether this value is 1 or not. If n equals to 1, we can just have this case as the trivial case, because the binary equivalent of 1 is always 1. So we can just go on and print 1 and can terminate the recursion. And you can just return back to the caller and terminate the recursion. Otherwise, if it is not, then we need to find out the binary equivalent of n by 2. That should be done first. So dec to bin, it should first find out the binary equivalent of n by 2. If that is printed, then we can just go on and print n% 2. So here we are done. That means in this case you can see that it's, if I say I pass on, let me just type this, say I pass on dec to bin and I'm passing on say 10, it will print 1010. That's the binary equivalent of 10. Let me show you that, then I'll explain. Oh, that's because of the fact that I have used this \n. I'm running again. Here you go. You can see that it's 1010. That's the binary equivalent of 10. So if you write 12, it's going to be 10. It's 1100. That's the equivalent of 12. So how we are solving this? Actually, say it's 10. Then what we are doing here? First call here it is 10. So we are just going and finding out the binary equivalent of 10 by 2. That's 5. And that is printing 101. And then on coming back from that recursion, we are finding 10% 2, that is 0, and we are printing 0. Now in this next call, when it is receiving 5, it's actually 5 by 2. We are actually printing, in order to print the binary equivalent of 5, what we are doing, we are calling dec to bin in order to print the binary equivalent of 2. 5 by 2 means that's 2 integer division. So this particular call 5 by 2, when you passed to this dec to bin, it's printing 10 because that's equivalent of 2. And then on coming back, what we are doing, we are finding out 5% 2, and that is 1. So in this way, when it ultimately reaching n equals to 1, it's actually printing 1 and returning back to the caller. So you can see that we just did a simple recursion and we are printing the binary equivalent of decimal number, and we are not implementing a stack by ourselves. Had we not used this recursion, we would require to write the push and pop operation for a stack and the stack itself in order to convert the decimal value to the equivalent binary. So here the number of lines of code is really very less. Otherwise, if we would adopt the iteration technique, it would be really large, because stack creation, maintenance, push, pop operations would have to be written by ourselves. So when you need the explicit stack, it's better to go with the recursion. And in each recursive call, we will be using the stack, the system generated stack, in order to push the value into the stack. Here you can see that we are using the system generated stack, because when this particular function is called recursively, the current n is pushed into the system generated stack, and when we are getting back, we are popping the system is popping the stack and getting the actual value of n for this instance and using that. So you don't need to write the stack at all when we are using recursion. So it's beneficial to write recursion when we need explicit stacks. With this, we come to the end of this discussion, and in the next tutorial I will be showing you some more example on recursions. Thank you.